Welcome back to the course of chemical crystallography. In the previous lecture, we started understanding the direct methods, different mathematical routes to determine the phases. So, during that discussion, we just discussed about the expressions for normalized structure factor, which is, you should remember, we discussed it as, we wrote it as EH equal to 1 by sum over j equal to 1 to n fj square root of that, and sum over j equal to 1 to n fj exponential 2 pi I hxj plus kyj plus lzj. So, and then we went on to define the corresponding unitary structure factor UH. You remember that when we write UH, it actually means we are talking about a reflection of Miller indices HK and L. So, we wrote that UH is equal to the mod of FH square divided by the sum of j equal to 1 to n fj. And then we understood that the value of UH varies from 0 to 1, and further we could write that EH square is equal to n UH square. So, we could write an expression between the normalized structure factor and the unitary structure factor. So, from that point we went on to explain two different methods. The sigma 1 relationship, which we then used to draw the Bragg-Leibson plots and tried to identify the electron density regions where the electron density is maximum for a given reflection and its family, that is 100 and 200, like for example if it is HKL, then 2H2K2L type of reflection, where should the more intensity region or more electron dense region should appear. So, what we saw that the regions where we have the overlap of maxima regions have the most probability of finding the atoms or electrons close to those regions in the unit cell, and this could lead to a reasonable structure solution when we do it in 3 dimension and do it for a large number of sets of planes which are parallel and intersecting set of planes. So, then we all went on to talk about the triplet relationship, where if you know that the EH and EK, that is the normalized structure factor for two different planes are both high, and we then identified those planes as H and K and they intersect at a given point. So, we understand that the point of intersection of these two planes, which give large values of E, would have the concentration of electron density at those regions where these two planes interact. So, then the plane which contains these large density points, which joins those large electron density points, are actually the plane which is nothing but h bar k bar in 2 dimension, or in case of HKL it could be h bar k bar L, that plane which then contains the larger electron density region. So, from this relationship one could conclude that h bar k bar will also have the large intensity. So, all these understandings give us an indication that how the large values of E can lead to the and guess of the actual location of atoms, but it only talks about the closeness or proximity of those atoms to these planes. The direct methods are a list of methods, a large number of different methods, which we will discuss a few of them, have been used for a long time. So this is most widely used method for direct determination of phases of reflections through various mathematical reasonings and understanding. Between 1930 and 1965, many attempts were made for direct phase determination, like the Bragg-Lipson plot and so on. The most important introduction or discovery in this region is by Harker and Caspar, who introduced the Harker-Caspar inequality to relate the phases of individual reflections. So the reference here is given for Harker-Caspar inequality. So for using Harker-Caspar inequality, one can write that FHKL square is less than equal to F000 square, where F00 is the amplitude of structure factor at the reciprocal lattice origin. This is nothing but equal to the total number of electrons present in the unit cell. So we write this equation as equation number 1. So this expression can be then modified for centrosymmetric structures as the following, which we can write as the equation number 2. FHKL square is less than equal to F triple naught into half of F triple naught plus half of F 2H 2K 2L, and this we write as equation number 2. So now if we assume that small UHKL is equal to FHKL by F000, and then we divide the equation number 2 by F squared 000, one can write that FHKL square by F000 square is less than equal to half plus F2H 2K 2L by F000 square into F000. So we can write it as UHKL square is less than equal to half plus half of U2H 2K 2L, and we write it as equation number 4. If both the magnitude and sign, the positive sign of UHKL square is known, then the phase of U2H 2K 2L remains to be the only parameter that has to be determined. So thus you can write mod of UHKL square is less than equal to half plus minus half U2H 2K 2L as equation number 5. So, if both UHKL and UE2H 2K 2L, that is this and that, are large, then positive sign on the right hand side is valid to make the inequality work. So, here is one example of this set of values for phase determination by inequality method. Here what we can see is that if I have the values for UHKL square listed in the first column and the calculated U2H or observed U2H 2K 2L square values are listed in second column, then the phase is, if it is positive, then you get the value of inequality on the right hand side is 0.6, and on the other hand if it is minus you get it as 0.4. What we should keep in mind that we are talking about the relationship where UHKL square should be less than equal to half plus minus half of U2H 2K 2L. So, we have various values of UHKL and U2H 2K 2L from the data, and we are trying to find out what should be the phase of U2H 2K 2L reflection compared to UHKL reflection. So, if these are the values which are listed here for UHKL, and if these are the values for the reflection U2H 2K 2L, then by selecting plus or minus we get different sets of values for the right hand side. These are the values for the right hand side. So, now we can see that if this is the condition, these are the values, then U2H 2K 2L must be positive, must have a positive phase to have the inequality valid. If it is second one, it also must be positive, but in case of third one, the phase can be both positive and negative. Similarly, for the next one and the following, this should be positive, and U2H 2K 2L could again be positive or negative for a smaller value of UHKL like this. So, this indicates that there are indications of possibilities of phases of different reflections related to one given reflection UHKL. So, to obtain a definite result, the reflections must have amplitudes that are large fractions of f. So, the larger the value of UHKL, it becomes easier to assign the correct phase of those reflections. But unfortunately, the reflections with large UHKL is less in number in general for all data sets, and hence this method becomes less useful for complex structures with large number of atoms. Further, UHKL, which is dependent on FHKL, is dependent on sin theta, and hence at high angle, that is at high sin theta, UHKL is generally small and cannot be used for phase determination purposes. That means the data that we collect is up to say 50 or 60 degree to theta, but UHKL values fall off rapidly at higher angles, and then those reflections will not have a significant value of UHKL, and we won't be able to determine the phases correctly. So, as the value of FHKL or UHKL reduces with sin theta, FHKL by F triple naught falls so low that the phase determination becomes impossible. So to overcome this, what we do is we assume that all the scattering power of an atom is concentrated at a point. So we consider it as a point atom and represent the F for such assumption as F atom. And then this assumption leads to the fact that the scattering power of F is independent of sin theta and is a constant for all values of sin theta by lambda. So with this understanding, if we try to plot the scattering factor Fj with sin theta by lambda, in general case Fj should fall like this with sin theta by lambda, that is for F for actual atom. But by considering the point atom, the value of F should remain constant, that is F point atom should be equal to Z for all values of theta. So in this case, we can write F equal to sum over j equal to 1 to n Fj e to the power 2 pi I hxj plus kyj plus lzj as equation number 6. And then if we assume that the structure is consisting of only one type of atom, then the scattering factor F can be taken out of the summation and we can rewrite it as j equal to 1 to n e to the power 2 pi I hxj plus k yj plus lzj as equation number 7. So one can then write that F equal to small f multiplied by E, where E is the sum of all exponential terms. So now as we know that the scattering factor F is equal to F0 e to the power minus B sin square theta by lambda square for real atom, we should write F equal to Z for point atom. So we can then write that F point by F real is nothing but ZE divided by E into F0 e to the power minus B sin square theta by lambda square. So this is my equation number 11. So from here we can write that F point is equal to Z by F0 e to the power minus B sin square theta by lambda square into F real. That is my equation number 12. As most of the structures contain more than one type of atoms, then the same expression has to be changed in this manner. F point is equal to sum over j equal to 1 to n Zj divided by e to the power minus B sin square theta by lambda square into sum over j equal to 1 to n fj foj into f real. So we write it as equation number 30. So now we will define again the unitary structure factor UHKL as FHKL point divided by F000, which is equation number 40. So using equation number 13 and that j equal to 1 to n zj is equal to f triple naught, we can write UHKL is equal to FHKL point divided by e to the power minus b sine square theta by lambda square into sum over j equal to 1 to n Foj. Or we can further simplify and write UHKL is equal to FHKL point divided by sum over j equal to 1 to n Fj, where this Fj includes the thermal motion, that is B. So we write this equation as 16. So as this U actually represents a structure factor HKL, so these must have the same phase and the value of U should range from 0 to 1. So that is the restriction on values of 0 to 1, and the UHKL would represent the structure factor with structure factor FHKL with the same phase as that of U. So this indicates that the complete in-phase scattering can occur only when the atoms are located at the maxima of Bragg-Leibson chart in 3 dimension as well. Although this will not actually locate the positions, that is the coordinates of the atoms, but will reduce the number of possible positions or sites of those atoms, and we will be able to identify the more electron density regions in the unit cell. Generally, U close to 1 are very less in number, which we have already indicated in the previous few slides, but large values of U allows us to use more constraints on atom positions. We know that the information contained in a reflection is determined by the intensity of the reflection relative to the average intensity of neighboring reflections. So it is obvious that U's are large, close to 1 for reflections, with higher value of sin theta compared to F for many low angle reflections with low sin theta. So this is the possibility. So to address this question that which reflections are most important, we need to arrange the reflections with decreasing value of mod U, that is the absolute value of U. This can be done by summation of U over all the atoms. So one can do this sum as UHKL is equal to 2 times j equal to 1 to n nj cos 2 pi hxj plus kyj plus lzj. This is equation number 17. This is valid for centrosymmetric structures. You have only one cos term that is valid for centrosymmetric structures only, where we can also write nj is equal to fj divided by sum over j equal to 1 to n fj. So this is the scattering power of the jth atom. As nj is a function of sin theta, we assume all atoms are same, which is not inappropriate for light atom structures having only carbon, nitrogen, oxygen and hydrogens in the structure. So we can further write that nj is equal to 1 by n. Similarly, the expectation value of f square is equal to sum over j equal to 1 to n fj square. So the expectation value of u square is given as sum over j equal to 1 to n nj square. So the RMS value of u, that is u RMS, is nothing but equal to sum over j equal to 1 to n nj square. So for light atom structures with similar Z, we can further write that URMS is nearly equal to 1 by square root of n. So as the average value of U drops well below the value needed for using the inequality to work for structure determination with large n, therefore we need better methods to determine the phases based on certainties and than probabilities. To overcome that, Karl and Hoffman in 1956 introduced the concept of normalized structure factor, where EHKL was represented as EHKL square is equal to UHKL square by expectation value of U square. This equation is number 24. So the E values are now allow the normalization of all classes of reflections to a common basis. So when we combine these two equations 24 and 21, we can write that EHKL square is equal to UHKL square divided by epsilon sum over j equal to 1 to n nj square and EHKL square as equal to mod of FHKL square divided by epsilon sum over j equal to 1 to n Fj square, where this epsilon is equal to an integer which is generally 1, but may be different for different space groups. So for example, in case of P21 by C space group, epsilon is equal to 2 for the HOL set of reflections and 0K 0 set of reflections, and epsilon is equal to 1 for all other HKL.